Assalamualaikum warahmatullahi wabarakatuh. My name is Ahmad Amir bin Ahmad Shuhairil and I'm from Group 2. This is the list of my group members. Today I'm going to talk about titanium trichloride as catalyst. Okay, now, before we proceed with the details about titanium trichloride, let's look at the physical properties first. For your information, titanium trichloride is actually one of the most common halides of titanium. As we can see on the right side of the slide, this is actually the molecular structure of titanium trichloride. Moreover, it has physical appearance of red-violet crystal hygroscopic, which has a density of 2.64 grams cm cubic, melting point of 425 degrees Celsius, boiling point of 960 degrees Celsius, and it is also soluble in water and acetone. The molar mass is 154.225 gram per mole. Okay, now, how is titanium trichloride formed? Titanium trichloride is usually produced by reduction of titanium 4 chloride. This is the chemical reaction. Two molecules of titanium 4 chloride will added by hydrogen gas and produce two molecules of hydrochloric acid plus with titanium trichloride. Okay, next, the applications of titanium trichloride in the industry. Titanium trichloride is the main Ziegler-Natta catalyst, which related to our topic, which is titanium trichloride as a catalyst. It is responsible for most industrial production of polyethylene. For an example, plastic. Polyethylene is a linear man-made polymer primarily used for packaging. The catalytic activities depend strongly on the polymorph, an inorganic object that takes on various forms of the titanium trichloride and the method of preparation. The next point, polyolefins are a type of polymer produced from a simple olefin as a monomer. For examples of polyolefins are polyethylene and polypropylene. This is the chemical reaction to produce polyethylene. Ethylene will undergo polymerization, which use titanium trichloride as a catalyst for the reaction.
Hi there, I'm Azia. Now I'm going to continue the slide. The next slide is about the process of polymerization of ethylene. For your information, this process is called the Ziegler-Natta-Polymerization is because it is conducted by adding the Ziegler-Natta catalyst. So it is all started from pumping the ethylene gas under a pressure into a reaction vessel where it polymerizes under the influence of a Ziegler-Natta catalyst in the presence of a solvent. Second, a slurry of polyethylene, a reacted ethylene monomer, catalyst, and last one, solvent, will exit the reactor. Third, unreacted ethylene is separated out and returned back to the reactor. Meanwhile, the catalyst is neutralized by an alcohol and will be washed and filtered out. Fourth, the excess solvent is recovered from a hot water bath and recycled back, but at the same time, a dryer dehydrates the wet polyethylene to its final powder form. So let's go to the previous slides. So here are the whole process of polymerization of ethylene, where it includes the Ziegler-Natta catalyst. So for my previous explanation, this all started from here. The ethylene gas is pumped out and goes into the reactor, but at the same time, the Ziegler-Natta catalyst and solvent are also entering the reactor. Therefore, there will be three substances in the reactor and will be stirred by the mechanical stirrer. After that, the four substances, which are the polyethylene, the ethylene that's already polymerized, the unreacted ethylene, the Ziegler-Natta catalyst, and the solvent, will exit out from the reactor. So from these four substances, the unreacted ethylene will separate it out and goes to the compressor. After being compressed, it will return back to the reactor. After that, from the three substances that are left, the catalyst will pass through here. It will be neutralized by the alcohol before entering the filter. Then it will filter and washed out as the deactivated catalyst. So moving on, the solvent enters the hot water bath. So it will be recovered here and recycled back to its origin. But at the same time, the polyethylene, as it exits from the hot water bath, so of course it will be wet. So the dryer will dehydrate the polyethylene and produce the dried polyethylene. So this is the last form of polyethylene. That's all from me. Next slide will be explained by my next groupmates.
Hello, I'm Izzati, and today I'll be giving a brief explanation about Ziegler-Natta catalyst. So what is a Ziegler-Natta catalyst? Well, a Ziegler-Natta catalyst, named after Carl Ziegler and Julio Natta, is a catalyst used in the synthesis of polymers of 1-alkenes, also known as alpha-olefin. These catalysts have been used in the commercial manufacture of various polyolefins since 1956. The Ziegler-Natta catalyst includes many mixtures of halides of transition metals, especially titanium, chromium, vanadium, and zirconium, with organic derivatives of non-transition metals, particularly alkyl aluminium compounds. The Ziegler-Natta catalysts are divided into two classes, which are the heterogeneous supported catalyst and homogeneous catalyst. So how does Ziegler-Natta catalyst works? Ziegler-Natta catalysts, which contains titanium trichloride, are remarkable for their ability to affect the polymerization of olefins, which is hydrocarbon containing a double carbon-carbon bond, to polymers of high molecular weights and highly ordered stereoregular structures. So this is one of the examples of how olefins turn to polyolefins, which is ethylene turning to polyethylene. And the catalyst used is a Ziegler-Natta organometallic catalyst, which is titanium compounds with an aluminium alkyl. A typical Ziegler-Natta catalyst system usually contains two parts. The first part is a transition metal compound, which is grouped for metals like titanium, zirconium, hafnium. The second part is an organoaluminium compound, which is a co-catalyst. The common example of Ziegler-Natta catalyst system includes TiCl4 plus Et3Al and TiCl3 plus Al-Et2Cl. The catalyst can give linear alpha-olefin polymers with high and controllable molecular weights. Moreover, it makes the fabrication of polymers with specific hapticity, meaning the stereochemical arrangement of the units in the main chain of the polymers possible. As you can see in the example given, when we use the catalyst, it will produce a polymer with specific stereochemical arrangement, as you can see in the example. And by controlling the stereochemistry of products, either syntactic or isotactic polymers can be achieved. And this is the end of the intro on Ziegler-Natta catalyst. So I will pass the baton to my friend Huyin for the next part.
Hi everyone, I'm Huyin and I'm going to explain about the mechanism of Ziegler-Natta catalytic polymerization. So there are mainly 4 steps of how the catalyst system works. The first step is the activation of Ziegler-Natta catalyst. The second step is the initiation step. The third step is the propagation step, and the final step is the termination step. So this is a diagram of how the polymerization process works with the help of Ziegler-Natta catalyst. So propylene is the monomer and polypropylene is the polymer. So if the monomer is the ethylene, then of course the polymer will become polyethylene. So this is the process of polymerization. The first step is the activation of Ziegler-Natta catalyst. The catalyst is activated by the coordination of triethyl aluminium to titanium atom. A titanium atom is surrounded by 1, 2, 3, 4, 5 chlorine atoms with one empty orbital here to be filled. When triethyl aluminium reacts with the titanium atom, it donates an ethyl group to the titanium atom, and the aluminium atom is coordinated to one of the chlorine atoms from the titanium atom. Thus, the catalyst system still has an empty orbital here to bind with the other molecules. The second step is the initiation step. The polymerization reaction is initiated by forming alkane metal complex. The formed alkane metal complex goes through electron shuffling with several pairs of electrons shifting their positions. So this is a diagram of the formation process of alkane metal complex. After electron shuffling, titanium atom has an empty orbital again, which is here, needing electrons to fill it. So the titanium atom will become more eager to bond with the other molecules. The third step is the propagation step. The process repeats when more propylene molecules react with the titanium molecule to form a polypropylene molecule. So this is the propylene molecule and this is the titanium molecule. This is the diagram of propagation of propylene towards polymeric chains of the titanium molecule. So the last step is termination step, which is the final step of a chain growth polymerization. It forms desired products such as polypropylene if the monomer is propylene and polyethylene if the monomer is ethylene. So this is a diagram of how the polymerization works at the last step, which is the termination step. So now I'll show you guys a video about how the Ziegler-Natta method works. Okay, so hopefully you guys can understand more about our topic, which is titanium trichloride as catalyst. We have reached the end of our video presentation, and the conclusion of our topic is Ziegler-Natta catalyst, which is titanium trichloride, has provided a worldwide profitable industry with production of more than 160 billion pounds and creation of various useful products such as polyethylene and polypropylene, which are the top two widely used synthetic plastic in the world. The creation of Ziegler-Natta catalyst by Carl Ziegler and Giulio Natta has largely improved people's lives and therefore won them a Nobel Prize in Chemistry in 1963. So these are the references for our video presentation and presentation slides. Thank you for your attention, and that's all from our group. Stay safe and have a nice day. Thank you.